Welcome. In this video, we're going to talk about stress and strain. So strain and stress are both very important fundamental concepts. Strain is the easier of the two to understand. So you hear about people being under stress or stressed out or under a lot of strain. That's not what we're talking about here. We're talking about very exact numbers, very exact physics, very exact quantities that you can go and measure out in the real world. They have specific definitions, and I'm going to be using the definitions that engineers use. So strain is the simpler of the two to understand, and all strain is the change in the length of something when it's either growing due to being stressed with load on it, or due to a temperature change, due to a moisture change, or any other phenomenon. That change in length divided by its original length, that is strain. So for instance, if we have this red bar here with an original length of L, and it's pulled apart and stretched by this force F. Right now, we don't care too much about what exactly that value of force F is, but it is being pulled apart in a positive strain. It means it's growing, so it's getting longer. So you're pulling on it, just like this stretchy thing. I'm pulling on it. It's under positive strain. It's under tension. It's under positive stress. So it's being pulled apart. Original length, new length. So this new length is longer. This original length got delta, this Greek delta, longer. You see delta everywhere in engineering. It usually is just a change. So L is the original length plus delta, that's the new length, if you want to know what that new length is. But the definition of strain is just that change in length, which is delta, over L. Now this is a linear relationship. It's simplified. It's very useful though. Most of the time when you're dealing with engineering, especially when it comes to metals, the strains that you see in real life are usually less than 1%. Metal usually, it has some ductility, so it can stretch up to maybe 10% or so depending on the alloy. But usually you design to some really low strain level. It's just, metal doesn't move a lot. It's very stiff, and you typically see these low strains where all these crazy other phenomenon that can happen at high strain don't matter. Actually, something much softer, like this stress ball, it deforms so much that this is not easily represented in this way. But when you're designing something out of metal, out of wood, out of plastic, something relatively stiff compared to this ball of rubber, the strains involved are very small. So this delta over L is usually 0.01, 0.001, a percent, a tenth of a percent, or something like that. But that's all strain is. Change in length over the original length. Engineering strain, that's all it is. Stress is an entirely different quantity. Stress is simply a force divided by an area. It's typically positive when it's under tension. So right here, this is a positive stress. I'm pulling on this. It's under tension. And I'm squeezing this ball. That's a negative stress. But their point is, it's a force divided by an area. So this force comes from whatever forces are acting on it. And this area is the cross-sectional area of what is actually experiencing the strain or what is actually experiencing the force. In this simplified example, I have this bar and I'm giving it this rectangular, actually a square cross-section, because its sides are both length h and h. So this entire bar is being put under the force F. Its area is h squared because each side is length h. So area is h squared. Its stress will be F divided by A. In this case, for this bar, it is F divided by h squared. So that right there shows one instance of how geometry is incredibly important to things, especially when it comes to stress. The stress involved is dependent on the area, which is a function of the geometry of the object. If this was a round cross-section, there would be a different formula to calculate the area. If it was any other cross-section, you'd use that formula for area. So this is why the shape of things that you design really matter when it comes to stress. Now, there's a relationship between stress and strain. So while strain is a measure of how much something changes in length, stress is a representation of how much force that material is under. Stiff materials do not move a lot for the amount of stress they are under. Flexible materials move quite a bit with very little force. So this would be an example of a flexible material. I don't really have to squeeze hard, and it moves a lot. If this were a ball of aluminum, you wouldn't even be able to see. I could squeeze as much as I want, you would never see it. Aluminum is way stiffer than this flexible stress ball. So the way it is represented is stress is equal to strain times E. E is the modulus. So this E is a function of the material. This strain is something that you measure. And this sigma, this Greek sigma, which is the stress, is a representation of how much force the object is under. So you can also change this relationship so it's sigma over E is equal to strain. In this case, I have a given stress and I have a given material value, and it gives me a strain. So if I need something that's very stiff, if I know something has to be just as big as this marker, for instance, but I don't want it to stretch a lot when I load it up, I want a really high modulus material. I'm going to be forced to use something like a metal, like steel or aluminum, depending on how much I'm allowing it to stretch, because I want this value of strain to be small. If I want it to actually stretch a lot, if I want something the size of this to actually visibly move when I load it up and put some force on it, I want to use a less flexible material. I'm assuming that I'm keeping this area intact, meaning it's a solid cross-section of material. Regardless of what it is, I'm only changing material. The other way to do this is to decrease the cross-sectional area of this. If I decrease this cross-sectional area of this thing and I want to stretch a lot, that'll mean for the same material, there's less area, so it'll stretch more. That's one way to give it more flexibility. So you can play around with the material and you can play around with the geometry to affect the stiffness of things. So back to where we were talking before about the spring stiffness. If I have the strain of something, I have the stress, I have the modulus, there's another relationship here. Remember, stress is equal to force divided by area. So I can plug in this force and this area into this relationship with strain so that force divided by area times modulus is equal to strain. But strain is also equal to the change in length over the original length. That's interesting a bit. Because before we were talking about, in a previous video, we were talking about the spring constant of things. So we look at this, we have this length delta. This is what's actually going to change. This is the displacement that a bar or some kind of object experiences. So I can rewrite this equation one more time, so that force times L, which is the original length, over area times the modulus is equal to delta. It's getting a little bit closer to where I want it to be. Okay? So let's go back to where we're talking before. We have a spring. Spring is some kind of spring constant, and that is equal to a force divided by a displacement. So this is a representation of a stiffness. For a given force with a given displacement, it gives you a stiffness. So let's change this here. So if we have this straight bar, we can rewrite this equation. So F divided by delta, and all these need to be inverted. They need to go to the other side. So we just get A times the modulus, so the area times the modulus over the original length. That gives me a spring constant. So that is where the stiffness of things comes from in the terms of the last video, which is there is some function of geometry, there is some function of the material itself gives you a stiffness. And as we get more involved in designing things and why you need to change the stiffness of things, how you design things to have a given stiffness, it becomes more and more complicated as the geometry gets, because you can have bending, tension, compression, shear, and a bunch of other effects. But it comes down to stiffness is some kind of function of geometry and material. So if you have any questions, or if you have any suggestions or topics that you would like to cover and you want to know more about, please comment below, and I'll see you next time.